So the second example for divide and conquer which we will be looking at today is this algorithm called Karatsuba's algorithm for fast multiplication of integers. So again, I'll start by giving you some context. So if you have two n-digit numbers and you have to multiply them using the usual technique which we are all familiar with from school, what we'll do is we'll compute n squared partial products where each digit of the first number is multiplied with each digit of the second number, and you write those leaving the appropriate number of zeros. So you will have n squared partial products, and then you will add up those partial products. If you have any carryover, you will take it to the next column and so on and so forth. And basically you do n squared multiplications, and then you add all those partial products to give you the final result. Now what if your number is very long? Let's say you have two numbers each having 100 digits, 200 digits. Then your n square is going to be extremely huge, right? So your multiplication is obviously going to cost you a lot. Is it possible to do better? And again, is it possible to do better using divide and conquer? This was the question. So before we go into the actual algorithm, we will first see a little bit of math, what led to the algorithm or what is the logic behind it. So look at the first picture on the slide. So say we want to multiply two numbers each having two digits. So the numbers are A, B and C, D. So I like to clarify that A, B is not A times B, it's a number. So A and B are the digits. It is B in the units place and A in the tens place. Similarly with C and D. So A, B, C, D, we have two numbers. You want to multiply them. So if you look at the multiplication I've done here, this is a normal high school multiplication we are taught. You take the partial products of each pair of digits. You will get AD and BD. You will get AC and BC here, and you leave a zero here, usual thing. Now we add up the partial products. Units place you get BD. Tens place you get AD plus BC. And hundreds place you will get AC. So for simplicity we are assuming there is no carryover. If at all there is a carryover, that will go here or here and that will get added. But essentially if you have two numbers each of two digits, you have these four partial products, and your answer is going to be dependent mainly on these four products. So if you see, it will be AC into 100 plus AD plus BC into 10 plus BD into 1, because that's the place value. This hundreds place, this whole thing in the tens place, and this in the units place. So I think we all agree that if we know these four partial products, we can simply multiply with the appropriate powers of 10, add it all up and arrive at the final product. So if you have two numbers of two digits each, your answer mainly depends on these four partial products, and we can generalize that if your numbers are of n digits each, your answer will depend on n squared partial products. Okay, moving on. So as you saw, we need four partial products, that is four multiplication operations for these two digit numbers. Now multiplications according to your computer hardware are costly. So is it possible to find the answer with fewer than 4 multiplications? Can we bring that 4 down to at least 3? Is what we are going to see. Now you forget about Karatsuba, forget about divide and conquer, everything. This is pure math. So we need AC, we need BD, and then we need AD plus BC. So you actually need the sum of these two partial products. So it's okay if you don't know AD and BC individually, as long as you know the sum of those two, because that is what you need for your answer. So keeping that in mind, we are going to try a little bit of manipulation. So you compute AC as usual, you compute BD as usual. So I'll just reiterate that A, B, C, D were digits. So AC and BD are basically products of two digits taken at a time. And then instead of doing AD and BC, two multiplications and then adding them up, we are going to do two additions and one multiplication. So you do A plus B, you do C plus D, and then you multiply them. Why are we doing this? Now if you expand A plus B times C plus D, you will get AC plus AD plus BC plus BD. This is normal distributive property of addition and multiplication. Now this, as you can see, if you just do some slight regrouping, it is AC plus AD plus BC plus BD. So if you multiply these two numbers, you're getting one big number, which is the sum of 4 numbers: AC, AD, BC and BD. Now you know AC already, you know BD already. So AD plus BC is nothing but this product minus AC minus BD, which is the partial product you require. So I will repeat it just to make things clear. You have two numbers, each of 2 digits, and we saw that there are these 4 partial products: AC, BD and then AD plus BC, which is what our answer mainly depends on. Now instead of doing 4 multiplications, finding these 4 partial products separately and then adding up AD plus BC, is it possible to directly find the sum AD plus BC? So that one multiplication at least will be reduced for us. That's what we are trying to do. And why? Because multiplications for computer hardware are expensive. So AC, we need that individual term, so we compute it as such. BD, again you need that individual term, so you compute it as such. Then instead of doing these 2 multiplications, you do A plus B times C plus D. You will get AC plus AD plus BC plus BD. From that you subtract AC, which you already know, and BD, which also you already know. You will get this sum AD plus BC, which is what you want. So if you look at it, how many multiplications did you perform? Only 3. You did AC, you did BD, and then you did A plus B times C plus D. You did 3 multiplications and you got all the terms which are required for your final answer. So now that you have the partial products, it's a very simple matter of putting them together. AC into 10 power 2 and then BD into 10 power 0, the units place, and this product minus AC minus BD. So A plus B times C plus D minus AC minus BD, which is this thing, into 10 power 1. If you put that together, you get your final answer for AB into CD. That's what the basic idea or the basic math behind Karatsuba multiplication is. Now we looked at this example for 2-digit numbers, but it can be mathematically proved that the same thing extends for n-digit numbers also. So any number of digits your multiplicand and multiplier may have, you recursively divide it into halves. The first number is divided into 2 halves, A and B. Second number into 2 halves, C and D. Then you will do 3 multiplications. First AC, second BD, third A plus B times C plus D. Then you will combine them using the formula given here. AC into 10 to the power 2 times n floor division 2 plus this A plus B times C plus D minus AC minus BD, the same thing we saw here, into 10 to the power n floor division 2 plus BD, which is your sum 2. So the whole idea is you're dividing a number recursively into a left half and a right half. You are calculating 3 partial products. You are combining those partial products with appropriate powers of 10 to get your final product. And those partial product computation, so if you take the AC here and the BD here, again that will also be done by dividing that number again into halves and so on. Your base case obviously is when it is a single digit number, you will do normal multiplication and return the result. This is the crux of the Karatsuba algorithm.